Hello and welcome to another Java tutorial. In this tutorial, I'm going to discuss the most important topic in scientific computing, which is solving differential equations. And there are generally two types of differential equations. The first one and the easier one or the simpler one is ordinary differential equations. And the second one, which we typically deal with in physics, is partial differential equations, right? So ordinary differential equations, or ODEs, are simpler and easier to solve and understand, so I'm going to start with them. And what are ordinary differential equations? So ordinary differential equations involve only one variable, all right? You may have multiple functions, but they are all functions of one variable, which in physics is typically time, right? If we want to solve the equations of motion for a system of particles, for example, our independent variable is time, and then the other variables or the functions are the positions of the particles, for example, okay? So in the ordinary differential equations, we only have one basically variable, which means all of the functions are one-dimensional functions, all right? And the most important class of equations are linear first-order differential equations of the form y prime equals f of x and y, all right? Now this involves only one variable and one function, right? So the question is, we have x, we know the derivative as a function of x and y. So it's not just a function of x, because if y prime was given as a function of x, we just integrate it from whatever point to some other point, and then we find y, right? But the problem arises when we actually have y prime in the format of x and y, a function of x and y. So the y prime, the slope also depends on the y itself, the function itself. And any sort of solving the equation, differential equation, basically translates into some sort of integration, all right? Because integration is the opposite of the differentiation. So if I want to solve the differential equation, I have to do the opposite of that, which is basically doing some sort of integration. And again, the complexity here is that the derivative of the function is given in terms of x, the variable, and the function itself. This is the most general case, right? And there are a few very limited number of analytical approaches, and we cannot use these analytical approaches in a most general sense. So one analytical approach is the separation of variables. So y prime is dy over dx. If f of x and y can be separated into the multiplication of two functions, one of them, or the first one, g1 of x, only is the function of the x variable, and then the second function, g2 of y, is only a function of y. And then we can separate x and y. So we bring g2 on the left and dx on the right. We end up with dy over g2 of y equals to g1 of x dx. Now this problem at the moment is basically a simple integration, because on the left side, if we integrate, we only have the variable y, so we can integrate this. On the right side, we have only variable of x, so we can integrate, okay? And then we find an implicit equation of y, because here, when on the left side, when we integrate, we get another function, some expression which is a function of y. And on the right side, we get an expression which is a function of x. And the goal is to find y in terms of x. So it's an implicit equation which we can then solve to find y, okay? But this is very limited case. In most of physics problems or any sort of engineering problems, we won't be able to do this, all right? So in general, if we want to look at numerical ways of solving this differential equation, y prime equals f of x and y, right? There are two types of problems, right? One is the initial value problem, IVP, which tells us, okay, I have been given this equation, y prime equals f of x and y, and I also know the value of the function at some starting point. Let's call it x0. I know that y at x0 is y0. This is called the initial condition. Now I want to know the value of the y of x. at any given point after this x0, right? And in general, I should be able to numerically solve that, because if I know the derivative, I know how y is changing, because derivative by itself is just the rate of change. That tells me how fast or how slow the function is changing, right? That's the behavior of the change of the function. So I should be able to extract the information for the later times by knowing the value of the function at some point, and also knowing the information of how the function is changing. Now, another set of problems are called boundary value problems. This typically arises when the physical variable is not time, it's more like position, x, y, z. And even in the simplest case of y prime equals f, x, and y, right? The boundary condition, instead of initial condition, we can have a boundary condition that gives us a mix of x0, x1 at the end of the interval, or the point that I'm trying to find y, and y0 and y1. So y0 is the value of the y at x0, and y1 is the value of the function at x1, right? So we might not know y0 or y1, but we can be given something like this. So x0 and x1 are given, these coefficients m0, m1, n0, n1 are given, and we are told that okay, there is a general relation like this is established between the value of the function at x0, the value of function at x1, and x0 and x1, right? So this is a more general case than the initial condition. So in the initial condition is basically m1 is 0, n1 is 0, so we can solve for y0 in terms of x0. But in general, it might not be the case. We might have we might know the value of the function at the endpoint, which is the final condition instead of initial condition. So in general, we can have a boundary condition. That's a more general way of having like a condition to be able to solve, because in order to solve this y prime equals f of x and y uniquely, we need to know some sort of in addition to differential equation, we need to know another information, at least one equation that describes the value of the function at some point. We need to be able to have that. If we have that information, we can uniquely solve the equation. And if the value of the function is exactly at the initial point, we call this initial condition. If there is a mixture of the values of the functions at different points, it's called boundary condition. Okay? Now, if only y0 and y1 show up in the boundary condition, we call it a Dirichlet boundary condition. If the derivative of the function show up, instead of the value of the function itself, the derivative shows up, we call it a Newman boundary condition. If both y prime and y show up, we call it in general a mixed boundary condition, or Robin boundary condition, sometimes called mixed boundary condition. And again, boundary conditions have a more general sense when we are solving partial differential equations, and the initial condition has more general sense when we are solving ordinary differential equations. All right? And in classical mechanics, like solving for the motions of particles, we always end up doing something like initial value problem. Okay? In thermodynamics or classical electrodynamics or quantum electrodynamics, we typically have partial differential equations of positions in a space. So we have boundary value problems, okay? So we are given this ordinary differential equation. This is the most basic and the most general form of the basic equation, y prime equals f of x and y. And we are given the initial condition. And we already know that in general finding analytical solution is rare. So we are resorting to numerical solutions. But we want to have a numerical solution with very good accuracy. That's the key point. And there are common numerical approaches, and it takes a long time if we want to discuss all of the methods. But here I have put some of them, and there are two most important ones, and basically all the other approaches can be somehow derived from the ideas of these two. So Euler method, which is sometimes called the forward Euler method, this is the most basic one and the simplest one. Backward Euler method, which is which is a little bit more complicated than the forward Euler method, because it's an implicit method. It gives you an equation, and then you have to solve again for y to find the value of the function y. Midpoint method, it's explicit, so it gives you the value of the y at each point directly. Runge-Kutta, we are going to look at the fourth order Runge-Kutta, which most of the time is called RK4, Runge-Kutta 4. And again, all these methods, Euler, midpoint, all other methods are basically a subset or a special case of RK4, or Runge-Kutta in general. So for example, Euler forward method is Runge-Kutta 1, first order Runge-Kutta. Midpoint is kind of like a second order Runge-Kutta. And there are special cases again of the same Runge-Kutta family, which is Cash-Karp, Fehlberg. And I'm going to focus on Euler method, midpoint method, briefly discuss the midpoint method, and then also the Runge-Kutta 4. So RK4 has a very good accuracy, and it is commonly used in most of the frameworks, numerical frameworks. And one key point that we always have to keep in mind is that different differential equations in general, whether it's a partial differential equation PDE or ordinary differential equation ODE, depending on the type of the differential equation, we probably end up choosing different methods for solving the equation numerically, and we typically don't use the same method for any type of differential equation. And that has to do with the stability behavior of these numerical methods. If the differential equation is somehow causing, for example, the Euler method to have an ill-conditioned behavior, the behavior is not very stable, then we resort to other methods. Okay, so choosing which method to use depends really on understanding how the differential equation behaves. But in general, especially for ODEs, RK4 is a very good approach. It's commonly used. And if you want to look at the full list of methods, of numerical methods for solving differential equations, look at this Wikipedia list. So en.wikipedia.org/wiki/list of numerical analysis topics. So this is general list of all the numerical analyses. And there is a section which is numerical methods for ordinary differential equations. All right, so you can look at this, and it gives you a full list, and it directs you to the pages, Wikipedia pages, that have all the information on all the numerical methods. But again, Euler method, the forward method, midpoint method, and the Runge-Kutta fourth order, RK4, are the most common ones. Especially RK4 has a very good accuracy. The order of error is very low, so it has a very good accuracy. So we can mostly use RK4 for most of the ordinary differential equations that we encounter in physics, engineering, and other fields. Okay, and again, solving differential equations is kind of like doing some sort of numerical integration. But this is a more general problem than numerical integration, because in numerical integration, essentially this function f of x and y does not depend on y. We have y prime equals f of x, so y becomes the integral of f of x from some point to another point. Okay, for example, in that case, if I only have f of x and I am trying to solve the initial condition problem, y of a is given, then y at some point, y of x is just integral of f of x from a to x. Okay, so it's just numerical integration, but this is a more general problem than just numerically integrating a function. But there is a close relation and ties. All right, so the first method is Euler method, and it's very simple. It's like so simple that it's very easy to understand. And again, we have one-dimensional ODE, which means we only have one variable x, and we have a function y of x, and we are trying to solve the initial condition. Y of a is given, so at the beginning of the interval, y of a is given, let's say y0, and we are asked to solve this differential equation. But what does it mean when we say solving this differential equation? It means that if I give you any other point after a, I should be able to find y of that point, right? Let's say I want to find the y at some point like b, or I want to find the value of the function at any later point after a, right? So here's a diagram. Let's say this is some sort of our function that we are looking for, and at point a the value of the function is given, and we are asked to solve this differential equation, which means at a later point, let's say b, I want to know what the y of b is, and I should be able to do this for any point after a or before a, for what for that matters. Before a or after, we typically, because of the initial condition, we typically look at the points after a, right? So how do we do that? Let's say a is given, y of a is given. I have the equation y prime equals f of x and y, and I want to find y of b. B is a later point after a, right? So the way I do it, I discretize, again, some similar to numerical integration. I discretize this interval from a to b into n sub-intervals, okay? And then from a forward, at each point, I in those intervals, sub-intervals, I approximate y prime using a very simple, I'm going to write it down here, simple forward approximation of y prime, okay? And we know that for forward approximation of the y prime, the order of error is always h. It's a linear order, right? The accuracy is order. So in order to get a good accuracy, we have to have a very small h, but we don't worry about that because we have some tricks that we learned in the sequences and series about accelerating the convergence. So we don't need to worry about h being very small, all right? But we're starting with a very simple way of solving a differential equation. I discretize into n small sub-intervals, so I choose n points from a to b, and then let's call them x0, x1, x2, etc. And then at each point, I write y prime as an approximation y x plus h minus y of x divided by h. And h is the length of each sub-interval, and I'm doing a uniform partitioning, so the length of all the sub-intervals is the same, h, which is b minus a divided by n. N is the number of sub-intervals. So y of x plus h minus y of x divided by h is y prime, which is f of x and y. So if I rearrange these, I can find the value of the y at some later point, x plus h, which is the value of the y at some point, y of x plus h, f of x and y, and this y is evaluated at x, okay? So if I know the x, the value of the function at some point, I can approximate the value of the function at a very small step after that, all right? And we know that if I have, I increase, the error is order of h, or 1 over n, the number of sub-intervals, okay? And if I start from x0, which is a, and do this all the way to xn, which is b, I can find an approximation for b, for y at b, right? And then if n goes to infinity, I have infinite number of sub-intervals. This error goes to 0, so the approximation gives me so this approximation becomes exact in the limit when n goes to infinity. So what does all of this mean? It means that we end up with a sequence. So this is my function, x0 is a, given, y0, this is my initial condition, is given, and I'm looking for y at point b. B is a later point after a, okay? So I do a uniform partitioning from x0, which is a, to xn, which is b, and I create a sequence. This is very important. I'm creating a sequence that converges to y of b as n goes to infinity. and the nth term y of n is actually the value of the function, the approximation of the value of the function at b. All right, so as I increase n, I just increase the number of subintervals and I end up with this sequence y of n. So y1 at some point h is b minus a over n, right? y1 is at x1 and x1 is x0 plus h. y1 is y0 plus h times the slope at y0, which is f of x0 and y0. Remember, y prime is f of x and y. So I find an approximation for y1, and from here x1 y1 I find an approximation for y2, which is y1 plus h times f of x1 y1, and all the way to yn. So I start from here, draw the tangent line and go to x1, and then draw the tangent line, go to x2, etc., etc., all the way to yn. And as n goes to infinity, yn approaches yb. All right, so I have a sequence that converges to the value of the function that I'm looking for, right? So the problem, the Euler method basically boils down the problem, basically it summarizes the problem into finding the limit of a sequence. And because we know that if the function f of x and y doesn't have any singularity at b, it's well behaved, then y of b should exist. So this sequence should converge to a number, right? It shouldn't go to infinity, it shouldn't blow up or anything. So I have a sequence. I'm using a very simple approximation of the derivative to find the yn. The error is very large because it's proportional to 1 over n, right? So error is bad. So what I'm expecting here is that this simple approximation, and this is basically the simplest way of going about it, finding y of b. I'm expecting this sequence y of n to have a very slow convergence. Again, that's because of the error, which is 1 over n, right? But I already know the trick of how to accelerate the convergence, and because the error is 1 over n to some power, the behavior of the error, I just use the Richardson acceleration. Okay, so here's the code. We want to implement this Euler method, very simple way of solving this initial value problem in Java. So f of x and y, define it as a functional interface. All right, this is the way we do it always. So let's call it deriv function. Deriv function means the function based on x and y that gives me y prime. All right, and it has one public abstract method, value, and takes the x and y. All right, and then we define a sequence. Remember, yn is a sequence that converges to the value of the function at point b, and b can be any point after a, any later point, right? So we define a sequence that finds yn for a given endpoint b. All right, so here b is basically x1. I changed the name in the code here, so this x1 is basically my b. Don't confuse it with the x1 that I had here, right? It's not here, it's b, some later point after x0. x0 is my initial point a, and we're doing uniform partitioning. That's the whole point. Typically for solving differential equations, we don't do non-uniform partitioning. We don't do any quadrature method because it just gets way complicated. And if you recall, in the numerical integration, I said that for just purely trying to numerically integrate a function f of x, we actually prefer non-uniform partitioning because they always end up with a sequence that converges quadratically to the value of the integral, to the exact value. Any uniform partitioning always has a linear or sublinear convergence. You cannot ever get a quadratic convergence. And again, that's because the behavior of error is 1 over n or 1 over n to some power. So you cannot get away with linear or sublinear convergence. That's the problem. So we're doing uniform partitioning. Okay? So h is b minus a over n, So in the code, I'm writing a method Euler sequence, which means this indicates that this generates a sequence based on the Euler method, right? A yn sequence based on the Euler method. So if n is 0, I'm at the initial point, just so I return y0. y0 is a variable that holds the value of y at at x0, okay? Else, if n is greater than, and note that I'm using a multi-line lambda expression. So n goes to something, this is a lambda expression that returns a sequence, all right? And if you're not familiar with how we implemented the sequence in Java, go back and look at my previous lectures on sequences and series in Java. So we define x and start with x0. We define y. At y0, h is x1 minus x0 over n. Remember, n is an integer, but I'm converting it to double to make sure x1 and x0 are double, but I'm converting also h to n to double just for safety. And then we're going to create all this y1, y2, y3 all the way to yn. So it's a for loop from I equals 0, I less than n, I plus plus. Note that n is the variable of the lambda expression, all right? Because I'm looking for yn and I'm starting from y0. So y holds the value in each loop of the for loop. I get y0, y1, y2, etc. So y is y. So originally it's y 0, and then add the h times the function value at x0, y0, I get y1, all right? And now y is y1 plus h, the value of x, which is now x1, because in each loop iteration I add h to x. So now I'm y1 plus h times the function at x1, y1. It gives me y2, okay? And then now y is y2 plus, and x is x2. So y2 plus h times the value of the function as x2, y2, it gives me y3. So eventually after n loops, n iterations, I end up, the value of y is yn, right? This sequence. So I return y at the end, all right? So this is how I'm generating this Euler sequence, the yn sequence that is going to converge to the value of the function at x1 or at b, all right? And again, this is supposed to have a very, very slow convergence because of the order of the error. This approximation, the forward difference approximation for the derivative has a very poor error, order of h or order of 1 over n. But then I apply a Richardson acceleration, and you probably can guess third order or fourth order Richardson acceleration should give me a very good error, like 1 over n to the third power or 1 over n to the fourth power. So Euler method plus Richardson acceleration is that's all that there is about solving the ODEs using the Euler method, or basically trying to find a very simple way of solving the Euler method. We find the sequence, we accelerate it, and we get a very fast converging result. And here's one example. So in this example, y prime is minus y. So the function of f of x and y is minus y. It doesn't even depend on x. And the initial condition is y of 0 is 1. So at x equals 0 is 1. And the exact solution is e to the minus x. E to the minus x, right? So if I take the derivative, y prime is minus e to the minus x. So y prime is minus y. So it satisfies the equation. And y of 0 is 1. So it also satisfies the boundary condition. And this function dies very rapidly, right, as x grows. At let's say I want to find the value of the function at 0.5, and analytically the exact value is 0.60653066. And let's see how the Euler sequence does as we increase n. So this is the code, example 1 here for this is the code. So I define a deriv function, which is basically my f of x and y. And so x and y using a lambda expression, which makes life very easy to define the function. X and y goes to minus y, all right? So this is f of x and y. And then I create an object called ODE solver. So I create an ODE solver and implemented this Euler sequence method in it. ODE solver takes the function, the degree function, the x0. So let's write this down. So this is x0, the initial point, and then the y0, the value of the function at x0. Okay, so the initial condition, we can pass it directly to the constructor. And x0 is 0, the initial point, and the initial value is 1, right? And then I create a sequence yn, which is ODE solver dot Euler sequence, at which point, at which x is 0.5. So I create a sequence, a Euler sequence, that converges to the value of y at 0.5. Okay, so I'm looking for this, and I know that as I increase n, as I move forward in this sequence, I should get a better and better approximation for y of 0.5. All right. So let's plot this. So I create an array of indices. In general, it should be integer, but I just stick with doubles. New double. Let's say 100 terms. So I'm going to go from y0 to y100 in the sequence, right? And then yn values, new double, the length of the indices, and then for loop, indices I is I, and the yn values of I is yn evaluate at I. All right. And then I create a MATLAB chart. This is a figure object, and plot the indices and yn values, render it to create the GUI window. I turn the markers on, and then the x label is number of partitions, which is basically n, right? If we go back, n is the number of partitions that we do from A to B. Y label is y of 0.5 value, right? We're looking for that, and fig.show creates the window. All right, let's see how the convergence works. As I start to increase the number of partitions or increase n, we see that the value starts to converge. So obviously we see the convergence. But after even 100 points, the 100th term in this sequence yn, if I zoom in, you see the value is 0.6058. So we are still like, we have only how many, 2-3 digit decimal places of accuracy. So it's painfully slow. It's painfully slow. So how do we accelerate the convergence? We do, for example, a third order Richardson acceleration. So here's the error, because I already know the exact solution. So I just calculate the error and plot it on a log scale to see very small numbers. And as I put it here, Richardson acceleration is the key to higher accuracy. Why Richardson? Because we already know that all these numerical integrations, or basically this approximation of the y prime, has an error that behaves as h to some power, or 1 over n to some power. That's why it's suitable for Richardson acceleration. As you can see, after 100 terms, the forward Euler method, the one that I showed here, after 100 terms, it definitely converges, but it only has like 2 decimal places of accuracy. But as soon as I apply a third order Richardson, you see the error goes down very rapidly. So at 100, I get more than 3, 4, 5, 6, 7, 8 decimal places of accuracy. Now what you can clearly observe here is that as we accelerate the convergence at very large numbers, we always end up with some instability. I mean, the error is still very small, but it starts to oscillate and probably goes back up as we increase. That's why if you use a higher order Richardson, you should evaluate it at a smaller point, like 30, number 30 or number 20, something like that, okay? And here's a plot of the actual function e to the minus x, and the blue is the exact solution. And I'm using a fourth order Richardson on the Euler, forward Euler, and I evaluate the fourth order Richardson at n equals 100 at here. And it's pretty much giving us the exact result. And the last thing that I want to talk about in this lecture is, let's try to look at the speed, how fast it's solving this numerical solution. So So let's head to Eclipse. I have already created the ODE project here. In the ODE, this is my interface for creating the derivative function. So this is y prime equals f of x and y, and use as a lambda expression for very ease of use. And then this is my ODE solver. I have a derivative function x0 and y0. So I'm solving an IVP, initial value problem, right? So this class is solving initial value problem. And the constructor has a derivative function x0 and y0. And this is my Euler sequence. And I have a test class, test Euler. And in the example 1, this is basically y prime equals minus y, f of x and y is minus y, and I'm creating the Euler sequence for 0.5. So Euler sequence, we're looking for y of 0.5, at y at x equals 0.5. So we create an Euler sequence and then look at its limit. So let's do this. So let's create a timer, new timer dot start, and after finding all the values, timer dot end. Actually, let's okay, let's try to just look at the timer dot stop and timer dot show. This just looks at how long it takes to create the Euler sequence and then find all the values, evaluate the sequence. So I'm going to run example 1, 51 millisecond, okay? And as you can see, we have a very painfully slow convergence to the exact value. But it should converge. We definitely see the convergence. All right? Now let's try to get the Euler sequence and then Richardson it. Let's say a third order Richardson. What I want to see is how much more overhead in terms of computation time this transformation adds, right? Because because we know that this is very good in terms of reducing the error significantly. So we want to see how much time it adds to the overall execution. 53. And as you can see, now the convergence is extremely fast. You see, after only basically 8-9 steps, we're there. We don't need to go to 100 term. And this is pretty much the exact result. I mean, the error has 7 decimal places of accuracy. Okay, so this took 53 milliseconds, and if we just go with that, it takes 50 milliseconds. So 3 milliseconds is the difference, but as you can see, it's very well worth the effort. The 3 milliseconds is very well worth it because we get an enormous improvement in the error, right? We reduce the error a lot, like from 2 decimal places of accuracy to 7 or 8 decimal places of accuracy. Just doing a very simple Richardson transformation. A very simple transformation on our sequence, all right? So this was the first step in our journey to look at solving differential equations. Please stay tuned. I have more lectures to come with more details, and I hope you enjoyed this lecture, and I'll see you in the next one.